Here are your examples for Lesson 4 in Chapter 4, Linear Functions. You should know exactly what we're talking about in regard to linear functions because you understand both the words function and linear. Linear function is going to be a function that can be written in the form of an equation of a line. Please put some of this on your gold sheet. Sometimes functions are written using two variables, which we're very familiar with. One variable, usually x, represents the domain, and again we're going to think of that as input, and usually y represents the range, or in our case, output. When a function is written in this form, it is an equation. Like equations, functions can be represented in words, in a table, with a graph, and as ordered pairs. The graph of a function is the set of ordered pairs consisting of an input and the corresponding output. So let's take a look at what that means. In example number 1, they tell us that the school store sells book covers for $2 each and notebooks for $1. Tony has $5 to spend. The function y equals 5 minus 2x represents the number of book covers x and notebooks y she can buy. Graph the function. So now think about this for a minute. Y is going to be the notebooks, x is going to be the book covers, and we start out with 5 because we have $5 to spend. So we have $5 minus the money we spend on book covers. 2 times x will yield how much money we have left to spend on notebooks. So once we understand the equation, we can take a look at this, and first of all it says to graph the function. Notice that the first thing they do is they set up a function table. We have our input of x and we have an output of y, and here we have our rule. We're going to input 0, so we're going to have 5 minus 2 times 0, so in other words 5 minus 0 would be 5. 5 minus 2 times 1 would be 5 minus 2, that's 3. 5 minus 4 would be 1, and then 5 minus 6 would be negative 1. So we have some points to graph here. Lastly, we can graph these ordered pairs, and we have 0, 5, move left or right 0 and up 5 would be right here. 1, 3 would be right here, 2, 1 is here, and 3, negative 1 would be here. The next thing they wanted us to, once we get done graphing the ordered pairs, we can take a look at what her options are. So she can't buy negative amounts, so this doesn't make any sense here. So she can buy 0 covers and 5 notebooks, or she could buy 1 cover, 3 notebooks, or 2 covers and 1 notebooks. Those are her choices. One thing I'd like to point out here is that here was our original equation, y equals 5x minus 2x. We could rewrite that as y equals negative 2x plus 5. And we should be able to graph that immediately by going to positive 5 on the y-axis, which would be right there, and then we're going to use a slope of negative 2 over 1. So we're going to drop 2 over 1, drop 2 over 1, drop 2 over 1, and notice that it points out all 4 of our coordinate pairs. If we back this out, we can see that each of these was indicated by our down 2 over 1, our slope. Remember, although you can make a function table and graph a line that way, you can also use the y equals mx plus b form of the line just by shifting this a little bit in order to graph it that way. Please press pause and do letter A. Alright, so let's take a look at example number 2. We are asked to graph y equals x plus 2. So the first thing we can do is make a function table. We have an input of x, an output of y, and this right here is our rule. Our rule, of course, is x plus 2. So if we put in 0 for x right here, we would have 0 plus 2, and of course our output would be 2. And you can track each of the points here. It's quite easy. You're just adding 0 plus 2, 1 plus 2, etc. So you should have 2, 3, 4, 5. And then, of course, we can turn this input and output of x and y into coordinates x and y, like you see right here. Coordinates to plot, and we can put each of these on a coordinate plane. We would go to 0, 2 would be right here, and you can see the rest of them there. I would like to point out that another way you could do this would be to go to our original equation, y equals x plus 2 right here. Recognize that we have a positive 2 for our y-intercept, which is right here, and that our slope, we have y equals x plus 2. Remember, we can see that our slope is 1 over 1, so we're going to go up 1 over 1, up 1, right 1, up 1, right 1, and you can see that that is another way to draw that same line. The first thing we did is make a function table, have it, and then graph each ordered pair, and then draw a line that passes through each point, and that is all done for you here. The line is the complete graph of the function. The ordered pair corresponding to any point on the line is a solution of the equation y equals x plus 2. We can take a look at that so we can check any individual solution by putting that solution into our original equation. We have an x value of negative 2 should yield a y value of 0. So we put 0 equals negative 2 plus 2, and indeed negative 2 plus 2 is indeed 0, so we have a solution. Please press pause and do letters B and C. Okay, here's an important concept that I'd like to make sure you have in your notes and on your gold sheet. We can represent functions in many different ways. We can represent functions in words. We can do it in an equation. We can do it with ordered pairs. We can do it with a table, or we could do it with a graph. This is very much like what we talked about in the last chapter in all the different ways that we could represent an equation or the graph of an equation or a line, for example. In a linear function is a function in which the graph of the solutions forms a straight line, which we already talked about. Therefore, an equation in the form of y equals mx plus b is a linear function, and this is something that you should be very, very familiar with. Now, this is a new concept down below here, so make sure you understand this very well. A function can be considered continuous or discrete. These are two new vocabulary words you need to make sure you put in your notes. A continuous data can take on any value, so there is no space between the data values for a given domain, and then we would draw a line to show that. Discrete data have space between possible data values. Graphs of continuous data are represented by solid lines, and graphs of discrete data are represented by dots, or there would be a much better word for them to use here, points. So for example, like over here, this would be a set of discrete data, this would be a set of discrete data, this would be a set of continuous data. To further illustrate what we mean when we use those two words, this is a really important piece of information right here. Think of it this way. Continuous data, the number of ounces in a glass. For example, we could have 3.1 ounces of water in a glass. We could have 3, we could have 3.8, we could have 5, we could have just about any number. We could have 5.12. Whereas discrete data, it would be the number of glasses in the cupboard. You can't realistically have 1.5 glasses in your cupboard or 1.3 glasses in your cupboard. It really doesn't make sense. Another example would be the weight of each chocolate chip. You could have a chocolate chip that weighs 0.125 if you measured it that accurately. So any number makes sense there, whereas if we were talking about the number of chocolate chips in a bag, there would either be 1 chocolate chip or 2 chocolate chips or 115 chocolate chips or whatever the case may be. You can't have half a chocolate chip. Again, I know some of you are going to argue that sure you can, but we're talking about realistically. You can determine if data that model real-world situations are discrete or continuous by considering whether all numbers are reasonable as part of the domain. Remember, the domain is the input, the x value. So let's take a look at what that means. Each person that enters a store receives a coupon of $5 off his or her entire purchase. Write a function to represent the total value of the coupons given out. So in this case, we're going to let Y, which of course is going to be our output, represent the total value, remember this is value, of the coupons, and let X represent the number of people. So we have an input of X people. So if we input, let's say, 5 people, we would have 5 times 5 people. Our output would be $25 in value of coupons. So this is our equation, y equals 5x. Remember, it's output, y equals the slope, $5 per as our slope, times the input. The next thing we're asked to do is make a function table to find the total values of the coupons given out to 5, 10, 15, and 20 customers. So here are our customers, 5, 10, 15, 20. Our output will be right here. We'll talk about that in a second. And our rule is 5 times our input. So 5 times the input of 5 gives us our output of 25. 5 times the input of 10, output of 50, etc. And we can have all of our inputs. So if we were to make these into coordinates, we would have 5, 25. We would plot that. We would have 10, 50. We would plot that, etc. So the next thing they ask us to do is to graph the function. And then they ask, is the function continuous or discrete? And of course explain that. So first of all, we're going to graph the ordered pairs. We have 5, 25. Then here we have 10, 50. Then 15, 75, and 20, 100. Use the ordered pairs from the function table to graph the function. We did that. And now we need to decide, does any number make sense here, or are there only certain numbers that make sense here? And the answer to that is there can only be whole number amount of customers. You can't have half a customer. So the points are not connected because this is discrete data, not continuous. This is discrete. Please press pause and do letters D through F. When you do the table here, please use the values 1, 2, 3, 4, and 5 so that you can check your answers with the letters in the video.